Good day. Today, we will be analyzing data using Jamovi. So we will be analyzing data with Jamovi for the following statistical analysis: one sample t-test, paired samples t-test, independent samples t-test, one-way ANOVA, Pearson R, simple linear regression, and multiple regression. So the one sample t-test examines whether the mean of a population is statistically different from a known or hypothesized value. The one sample t-test is a parametric test. So here is an example. A research scholar wants to determine if the average weight of a student's everyday bag differs from a set value. Let's say this value is 25 kilos. So our null hypothesis is the mean weight is equal to 25 kilograms, and our alternative hypothesis is that the mean weight is not equal to 25 kilograms. Now let's go to Jamovi for the computation. So we have now here the weight columns. Okay, so let's click analysis. Then we go to t-test, one sample t-test. And we put here the weights as our dependent variable. Then we put the test value is 25 kilograms. So we put 25. And we select the test value is not equal since our alternative hypothesis is not equal. So this is a two-tailed test. So before we analyze this one, we first click the assumption checks. We have here the normality check, the QQ plot, the mean difference, the effect size, and the descriptives. So let's check first the normality test. The p-value for the normality test is 0.354. So this is above the significance level of 0.05. So this means that we passed the normality test. Okay, the samples passed the normality test. Okay, and in the QQ plot, as you can see, there are no outliers. So now let's interpret these results. So from the generated results, we can see that the p-value 0.841, since the p-value is not less than the alpha of 0.05, we fail to reject the null hypothesis. This means that there is no significant difference in the average weight of a student's everyday bag from a set value of 25 kilograms, since the average weight in this dataset is 25.1 kilograms. So the mean difference of 0.1 kilograms is insignificant. Okay? So next is the paired samples t-test. The paired samples t-test compares the means of two measurements taken from the same individual, object, or related units. These paired measurements can represent things like measurement taken at two different times, example, pre-test and post-test score, with an intervention administered between the two time points. Then a measurement taken under two different conditions, example, completing a test under a control condition and an experimental condition. And measurements taken from two halves or sides of a subject or experimental unit, example, measuring hearing loss in a subject's left and right ears. So here is an example. So the table on the left side gives data from a hypothetical study in which students were asked to rate a government agency before and after 1 week of viewing a 15-minute DVD of the agency twice a day. Use an alpha 0.05 for the test to determine whether there is a significant increase in the ratings of the agency after the 1-week video treatment. Assume the differences in ratings are normally distributed in the population. So because the researchers are testing to determine if there is a significant increase in ratings from before to after a one-tailed test is being conducted. The null and alternative hypotheses are. So the null hypothesis is that mu1 is equal to mu2, or the difference in mu1 or mu2 is equal to 0. And the alternative hypothesis is that mu1 is less than mu2, or the difference between mu1 and mu2 is less than 0, where the before measurements are population 1 and after measurements are population 2. So now let's go to Jamovi. So here we have the before and after results. So to analyze this one, let's go to analysis, t-test, paired samples t-test. So we select before and after as the paired values. Okay, so we select here that measure 1 is less than measure 2. Okay, so the mean difference, check the mean difference, the effect size, the descriptives, okay, the normality test, and the QQ plot. Okay, let's first check the normality test. So the p-value in the normality test is 0.978, which is above the significance level of 0.05. So this means that we passed the assumption check. And in the QQ plot, as you can see, there are no outliers. Okay, so meaning the samples are normally distributed. So now let's interpret the results. So the p-value obtained from the test is 0.022. The significance level test for the test was alpha equals 0.05. So since the p-value is less than alpha, the decision is reject HO. So with 95% confidence, the researcher rejects the null hypothesis and concludes that there is enough evidence to say that on average, the ratings have increased significantly. This result might be used by managers to support a decision to continue using the videos or expand the use of such videos in an effort to increase public support for their company. So as you can see, the mean difference is 5.86. So the mean before is 23.3 and the mean after is 29.1. So there is a mean difference of 5.86. So this is enough evidence to say that on average, the ratings have increased significantly. Okay, so next is the independent samples t-test. The independent samples t-test compares the means of two independent groups in order to determine whether there is statistical evidence that the associated population means are significantly different. The independent samples t-test is a parametric test. Okay, so here's an example. Suppose we want to conduct a hypothesis test to determine whether the average annual wage of two of the future careers of the students, say advertising manager, is different from the average annual wage of an auditing manager at a 5% significance level. So because we are testing to determine whether the means are different, our hypotheses are, so the null hypothesis is that mu1 is equal to mu2. And our alternative hypothesis is that mu1 is not equal to mu2, where advertising managers are population 1 and auditing managers are population 2. Now let's go to Jamovi. So we have here the position and the wage. So as you can see, the positions are all put in one column. okay, as well as their corresponding wage rate. Okay, so now let's analyze this one. So let's click analysis, um, regression, I know, t-test, t-test and independent samples t-test. Okay, so for our dependent variables, we have here the wage and the position as our grouping variable. Then we select the hypothesis group 1 is not equal to group 2. Then the mean difference, the effect size, the descriptives, the homogeneity test, the normality test, and the QQ plot. So the normality test, here the p-value is 0.794. So this is above the significant level of 0.05. So this means that we passed the normality check. And the homogeneity of variances test, the p-value is also above the significant level of 0.05. So this is check. Okay. And the QQ plot, so as you can see, there are no outliers. So now let's interpret the results. Okay. So the p-value obtained from the test is 0.021. The significance level set for the test was 5%, so alpha equals 0.05. Since the p-value is less than alpha, the decision is to reject HO. With 95% confidence, the researcher rejects the null hypothesis and can say that there is a significant difference between the average annual wage of an advertising manager and the average annual wage of an auditing manager. The researcher then examines a sample mean 70.7 for advertising managers and 62.2 for auditing managers, and conclude that advertising managers earn more on the average than do auditing managers. Okay? Next is the one-way ANOVA. The one-way analysis of variance, or the ANOVA, is used to determine whether there are any statistically significant differences between the means of two or more independent or unrelated groups, although you tend to only see it used when there are a minimum of three rather than two groups. So, for example, you could use a one-way ANOVA to understand whether exam performance differed based on anxiety levels among students, dividing students into three independent groups: low, medium, and high-stressed students. Okay, let's go to Jamovi. Okay, we have here three groups: Group A, Group B, and Group C, and the reaction time. So let's use this data. Okay, let's click Analysis, then ANOVA, and let's choose one-way ANOVA. Okay, so our dependent variable is the reaction time, and the grouping variable is the group. Okay, then we select descriptive table, the homogeneity test, the normality test, and the QQ plot. Okay, first let's check the assumption checks. So here in the normality test, so the p-value is less than the significant level of 0.05. So dito pa lang, bagsak na tayo. because the p-value is less than 0.05. So to pass the normality test, the p-value should be above the significant level of 0.05. So the homogeneity of variances test is more than 0.05, so here we passed. And then the QQ plot. So as you can see, so there are outliers. So before we analyze this one, since we did not pass the normality test, let's check first if there are outliers. Okay, so let's go to exploration, then descriptives. Then we put here the reaction time as the variables. Then we click statistics. Okay. Then we click here the plots. Then we check box plot. Oh, as you can see, the numbers here represents the outliers. So kaya pala, okay, so kaya pala bumagsak tayo sa assumption test. Okay, so let's check what are these numbers. So let's go to data. Okay, the numbers here represents the row number. So we have here row number 1. So row number 1, it's 165 and it is an outlier. And row number 8 is 170. So another outlier is row number 11, 165. Okay, another outlier is row number 23, that is 166. And lastly is row number 27, that is 165. So that's why we did not pass the normality test, because there are many outliers in the sample. Okay, so in this case, we will not use the parametric test one-way ANOVA. Let's use the non-parametric counterpart. So to analyze, let's go to Analysis, ANOVA, and the one-way ANOVA non-parametric. This is the Kroskal-Wallis. Okay, so let's put here reaction time as a dependent variable and the group as the grouping variable. Then we check the effect size and the DSCF pairwise comparisons. Okay, so here is the result. Now let's interpret the results. So using the one-way ANOVA non-parametric, the p-value obtained from the test is 0.119. The significance level set for the test was 5%, so alpha equals 0.05. Since the p-value is greater than alpha, the decision is to fail to reject the null hypothesis. So the p-value obtained from the DSCF pairwise comparisons are 0.998 for groups A and B, 0.195 for groups A and C, and 0.159 for groups B and C. This shows that there is no significant difference in reaction time across the three groups. So next is the person R. The bivariate person correlation produces a sample correlation coefficient R, which measures the strength and direction of linear relationships between pairs of continuous variables. By extension, the person correlation evaluates whether there is statistical evidence for a linear relationship among the same pairs of variables in the population, represented by a population correlation coefficient rho. The person correlation is a parametric measure. So, example, the National Safety Council released the following data on the incidence rates of for fatal or lost work time injuries per 100 employees for several industries in 3 recent years. Compute R for each pair of years and determine which years are most highly correlated. Okay, let's go to Jamovi. Then we have here year 1, year 2, and year 3. So we click analysis, regression, and then the correlation matrix. Then we select year 1, year 2, and year 3. Okay, then we click the we flag significant correlations. And we click the correlation matrix. So here, as you can see, so there is correlation. So this is now the result. Then let's interpret the result. So year 1 versus year 2. So it's year 1 versus year 2. The R is 0.975. Then year 1 versus year 3, the R is 0.957. Then year 2 versus year 3, the R equals 0.985. So a question may be, how do we decide how good the correlation coefficient is? So correlation measures the strength of the relationship between x and y. The closer the absolute value of r is to 1, the stronger the linear relationship is between the variables. Notice that the variables year 2 and 3 have the highest positive correlation coefficient. Thus, among the three, they are the most highly correlated years. Okay? Now let's go to simple linear regression. Simple linear regression analysis is a technique that is used to model the dependency of one dependent variable upon one independent variable. This relationship between these two variables is explained by an equation, y equals a plus bx, where y is the estimated dependent variable, a is the y-intercept, b is the slope, and x is the independent variable. So here is an example. Suppose the data displayed in table 12.3 are the costs and associated number of passengers for 12 500-mile commercial airline flights using Boeing 737s during the same season of the year. We will use this data to develop a regression model to predict cost by number of passengers. Okay, let's go to Jamovi. Okay, we have here the number of passengers and the cost. So let's click analysis, regression, then the linear regression. So our dependent variable is the cost. Our covariate is the number of passengers. Okay. Then we check the assumption checks, the autocorrelation test, normality test, the QQ plot, then the model fit, the F test. Okay, so in the QQ plot, so we have no um, outlier. And the assumption check, the p-value, which is 0.158, is above the significance level of 0.05. So this means that we pass the assumption checks. And the normality test also is above the significant level of 0.05. So this is again check. So since we passed the assumption checks, so let's now interpret the results. So here, the least squares equation of the regression line for this problem is y equals 1569.80. Here, this is the y-intercept plus 40.70x. So this is the slope, 40.70x. This can also be written as cost equals 1569.80 plus 40.70 times the number of passengers. And the r squared here, which is 0.899, means that about 89.90% of the variability of costs can be accounted for or explained by the number of passengers in the flight. So what is the interpretation of the slope coefficient b sub 1? So the slope of this regression line is 40.70. One interpretation of the slope in this problem is that for every unit increase in x, that is every person added to the flight of the airplane, there is a $40.70 increase in the cost of the flight. Then what is the interpretation of the intercept coefficient b sub 0? Is it practical to the given scenario? So the y-intercept is the point where the line crosses the y-axis, where x is 0. Sometimes in regression analysis, the y-intercept is meaningless in terms of the variables studied. However, in this problem, one interpretation of a y-intercept, which is $1,569.80, is that even if there were no passengers on the commercial flight, it would still cost $1,569.80. In other words, there are costs associated with a flight that carries no passengers. So what is the expected cost associated with a flight that carries 90 passengers? So using the estimated regression equation where x is equal to 90, we have y equals 1569.80 plus 40.70 times 90. So that is equal to 5232.80. So the expected cost for a flight with 90 passengers is 5232.80. Okay, so next let's go to multiple linear regression. Multiple linear regression is an extension of simple linear regression. It is used when we want to predict the value of a variable based on the value of two or more other variables. The estimated multiple linear regression formula takes the form y equals b sub 0 plus b sub 1 times x of 1 plus b sub 2 times x of 2 to infinity, where y is the predicted value of the dependent variable, x of I are particular values of the independent variables, and b sub I are the regression coefficients. So one example is this. A real estate study was conducted in a small city to determine what variables, if any, are related to the market price of a home. Several variables were explored, including the number of bedrooms, the number of bathrooms, the age of the house, the number of square feet of living space, the total number of square feet of space, and the number of garages. Suppose the researcher wants to develop a regression model to predict the market price of a home by two variables: the total number of square feet in the house and the age of the house. Listed in Table 13.1 are the data of these three variables. So now let's go to Jamovi. Okay, so we have here the market price, the total area, and the age of the house. So let's go to analysis, regression, then linear regression. So here we select the market price as the dependent variable, and the covariates are the total area, the age of the house. Oh, let's correct this first. The age of the house should be a continuous variable. Okay, so the age of the house. So that's it. Then we click the assumption checks, the autocorrelation, normality test, QQ plot, then the model fit, the F test. Okay, so here as you can see in the assumption checks, the p-value is above the significant level 0.05, so this is checked, as well as in the normality test. So this is also checked. And in the QQ plot, so there are no outliers. So now, okay, let's interpret this result. So the result generated here, so the multiple regression equation is y equals 57.35. So this is the y-intercept plus the 0.077 x of 1. So this is the slope minus 0.6663 x of 2 times x of 2. So this is the slope for the age of the house. Or y equals 57.35 plus 0.0177 times the total square feet minus 0.6663 times the age of the house. Okay, so interpreting the regression constant. The regression constant, that is 57.35, is the y-intercept. The y-intercept is the value of y if both x of 1, number of square feet, and x of 2, the age of the house, are 0. So in this example, a practical understanding of a y-intercept is meaningless. It makes little sense to say that a house containing no square feet, that is x of 1 equals 0, and no years of age, x of 2 equals 0, would cost 57,350. So interpreting the regression coefficient. The coefficient of x of 1, the total number of square feet in the house, is 0.0177, which means that a 1 unit increase in square footage would result in a predicted increase of 0.0177 times $1,000 equals $17.70 in the price of a home if age were held constant. All other variables being held constant, the addition of 1 square foot of space in the house results in a predicted increase of $17.70 in the price of the home. So interpreting the regression coefficients. So the coefficient of x of 2, the age of the house, is negative 0.663. The negative sign in the coefficient denotes an inverse relationship between the age of a house and the price of the house. So the older the house, the lower the price, of course. So in this case, if the total number of square feet in the house is kept constant, a 1 unit increase in the age of the house will result in negative 0.663 times $1,000, that is equal to negative $666.30, a predicted $666.30 drop in the price. So the interpretation of the R squared. So the value of the R squared is calculated to be 0.741. Okay. So we say that about 74.1% of the total variation in the market price can be accounted for or explained by the total number of square feet and the age of the house. So testing the overall model, based on the resulting p-value, our decision is to reject HO, to reject the null hypothesis. We conclude that at least one of the independent variables is adding significant predictability for y. Okay, so significance test of the regression coefficients. Observe that based on the p-values at alpha 0.05, we can say that both regression coefficients for the total square feet and age of the house are significant in the model. Okay, since the p-values are lower than 0.05. Okay, so next is using the multiple regression equation. So this regression model can be used to predict the price of a house in this small Louisiana city. If the house has 2,500 square feet total and is 12 years old, the x of 1 equals 2,500 and x of 2 equals 12. Substituting these values into the regression model yields y equals 57.35 plus 0.0177 x of 1 minus 0.6663 times x of 2. So y equals 57.35 plus 0.0177 times 2,500 minus 0.6663 times 12. So y equals 93.604. Thus, the predicted price of the house is 93,604. So this regression analysis is very useful to predict the price of a house. So this is used for prediction, okay, for predictive analysis. So as you can see, with all the tests that we have using Jamovi. So Jamovi is a user-friendly, open statistical spreadsheet designed to be as simple to use as possible, but still allow very sophisticated analysis. So it makes our life easier in doing our data analysis. Okay, so that's all. Thank you. Hope you learned a lot from our tutorial video today. Thank you and good day.